Good evening, everyone. My name is Mike McAllister. I work here at DMSI as a programmer. I should take just a moment to sincerely thank DMSI for providing the meeting facilities tonight. DMSI is really a great company to work for, and they are very generous in supporting my interest in doing this presentation. This is actually a hobby pursuit of mine, and not anything officially associated with work here. I do have an idea or two for future use of high-performance computing technology that might come into play, but for now it's just one of my hobbies. Perhaps a bit of background. I've been working with .NET technology since the first beta came out. I also spend quite a bit of my free time working with .NET in areas that interest me. One of those areas I'm really excited about right now is Microsoft's HPC server and its coding design patterns. At first glance, I didn't realize HPC was actually supercomputer architecture. I certainly saw the software listed on MSDN, but I didn't pay too much attention to it. I found out about it indirectly one day while researching Cray. On the web, I ran into this baby or mini supercomputer that can be purchased from Dell. It's a kind of joint project between Cray, Microsoft, NVIDIA, and Dell. It's Cray hardware, NVIDIA graphics processing, running Microsoft's HPC operating system, of course, and then finally marketed and sold by Dell. I mentioned briefly in a team meeting toward the end of 2010, I'd sure like to have one of these for Christmas. The top-end models go for about 90 grand. And then one of my co-workers made this empty box Cray for me and wrapped it up and gave it to me for Christmas. So I've been interested in this for a while. Now that you at least know Microsoft's HPC is software for supercomputer architecture, let's describe an HPC environment in both hardware and software terms before we move on to the details of the .NET application software for HPC. An HPC supercomputer cluster can be up to 1,000 machines. Each machine can theoretically be a large machine, though in practice today most of the time blade servers are used. The software requirement is either the machines must run HPC Server 2008 R2 or they may run 32 or 64-bit Windows 7. The desktop class machines are used as compute resources. More on that a bit later. In addition, all machines have a suite or a package installed named HPC Pack. When you have multiple machines running on a network, one of the very important performance factors is network latency. This is probably one of the main reasons blades are used in cabinets that are physically close together, so the networking can be optimized as much as possible. In this diagram, I have pulled the network pipe up out of the domain to highlight its importance. Typically, when these groups of machines are put together, high-speed networking topologies are used. Fiber channel over Ethernet, and 10 gigabit Ethernet would be examples. At home, where I built my cluster, I only have gigabit Ethernet, but then the majority of my cluster is actually created on virtual machines on one server, so most of the networking is really just CPU on that server. You start building an HPC cluster by creating an Active Directory domain for the cluster, separate from other domains if you have them. Then you add machines to that domain. The reason for a separate domain is because the machines within the cluster need to have trust between them. An easy way, I guess, to express this is just to say the machines need to have administrator level permissions and shared access. There are 3 categories of server nodes that all have HPC Server 2008 R2 installed. First, there's a head node, and there's only one of those. This server is the kind of the manager node of the cluster. We'll look at the cluster control panel a bit later when we demo a live HPC cluster. The second type of HPC server is called a broker node. One or more of these can be used to interface with services like WCF services or for interfacing with Microsoft's Azure. The Azure capability includes using resources in the Azure cloud for compute capability that is a remote extension of the local cluster. Azure usage can optionally include integration between remote and local domains. I played around with domain integration but found that my local 100 megabit network at the time, its performance, and my DSL internet connection were really just a bottleneck, so I've temporarily tabled that project. I really needed domain integration between Azure and my local domain because my software application that you'll see a little bit later requires all machines to be able to read and write to a common network share on the domain. The third type of server machine is the compute node. Most of the nodes in the cluster are of this type. Their role is that of worker bee. Just run the software assigned and let others manage the process. It's also possible to add 32 and 64-bit Windows 7 machines to the cluster and use their CPUs for compute resources. And just to make a note, it is necessary to have them added to the same cluster Active Directory domain. Okay, so now that we have defined the networking at least at a high level, the hardware, talked about it just briefly, and the OS software layers, let's begin to talk about HPC software, and that to me is the heart of the matter anyway. Probably the most important point here, or one of the most important points I'd like to make, is that in my own personal programming experience with HPC, I would say the thing that has surprised me absolutely the most is how approachable it is. Years ago, I remember looking into and thinking about creating a Beowulf cluster of machines. But at that time I was really put off by the complexity of the programming. At the time I could not convince myself I had a real need for learning message passing interface programming. It just seemed too difficult to me. But now with the C# libraries available for HPC, at least the relatively simple things I have done so far seem to be easy. They really are easy. Now, I don't want anyone to come away from this presentation tonight with any misunderstandings about what HPC can or cannot do, and that's the reason that I've made one paragraph here, one bullet point, bold italic. In my opinion, Moore's law in core silicon is coming to an end if it hasn't already. The multi-core era is upon us, but applications have to be written, or if they are pre-existing applications, perhaps rewritten in order to run across multiple cores. Running across multiple cores does not happen automatically, or easily for that matter, unless we can discern cases where the atomic nature of a process or a sub-process allows for simple parallel separation. Now, I spend most of my time on business application programming. Business applications which work with creating and maintaining data in a transactional scope are not very easy to parallelize. To me, this is one of the real challenges of the future of programming, and that challenge is to move everyday business process programming into the realm of parallel processing. One example of simple parallelization would be a blackjack game, and actually this is my main example to demo tonight. In running multiple hands of blackjack at once, there is no interdependence between individual games or hands, maybe other than the depletion of a deck of cards, which has to be reassembled and shuffled occasionally. In the HPC.NET 4 libraries, there is a particular task type called parametric sweep task, which basically means a repetition or cycle of parameters being passed. I guess think in terms of an array of processes, each with a unique identifier in the parameters passed. That's probably the easiest way to think about it. I'll show the details in a few minutes. Just to mention, and I'll try to do this quickly because it's certainly not really totally central to the topic tonight, but rather historical as far as my involvement in blackjack simulation. It goes back in time actually quite a ways. I spent a lot of my youth, 9 years old and up, as an amateur and eventually semi-professional magician. I particularly liked card manipulation magic. I'm certainly absolutely no gambler. I would not waste money on that kind of nonsense, but on the other hand, I do like to understand things at a fairly detailed level. Somewhere along the line, probably about 1990 or a little after, I got the idea I wanted to prove by example whether or not it was possible to win at blackjack, either using simple rules and decisions during a game or by counting cards, or both. So at that time I wrote an application in QuickBasic for playing blackjack, and then I also wrote a Clipper database program for storing the game playing rules and card counting options. I used that same 1990s version database, but I export it in real time as a delimited text file for the new HPC version that I'm going to demo tonight. That way I'm leveraging legacy code to set up the runtime environment for the blackjack simulation running on HPC. Moving right along, I've decided the best way to demo HPC, and what I've done is to kind of start at the bottom and work our way back up to the HPC operational level. This way we can look at some code soon, right away, and then see how the code operates as we continue. I split the HPC implementation of my blackjack simulation into two separate applications. One for the gameplay, and the other as a wrapper application that creates the required HPC objects which execute the gameplay application X number of times within a parametric sweep. Tonight I want to concentrate on the wrapper piece that I have named HPC Blackjack Lab Runner, because it is what is central to understanding an HPC parametric sweep task. Actually, I would say the blackjack game is really a secondary concern. It can be swapped out with about any task-based command line console type application just by changing part of one line of HPC code in the wrapper application. I guess another way of saying this is the wrapper application actually orchestrates running the other application repetitively in parallel, and Microsoft has really made this easy to do. Let's begin by looking at the wrapper application, the one called HPC Blackjack Lab Runner. This first view I've set up is a collapsed overview of the program class with the using statements expanded first. The only three using statements I would point out are system.directory services, which is used a bit later for domain lookup, and then also Microsoft HPC Scheduler and Microsoft HPC Scheduler properties. Those are the libraries that contain the parametric sweep task and associated objects and interfaces. You might notice here the entire program is only 200 lines or a bit longer. I think this brevity speaks to the work Microsoft has done and the elegance and simplicity of these solutions. I'm going to go ahead next then and expand the class level objects so we can look at those. My style, my own personal style, is to always prefix class level fields with the underscore character. That's an easy way to mark them so that you know when you're working with them in code that it has scope at the class. And most of these in this example are just simple numeric values used for grand totaling the blackjack statistics. There is one pretty interesting object here though, bears mention before we go on. It's an instance of manual reset event, and it comes from system threading actually. And its hover text says notifies one or more waiting threads that an event has occurred. We'll look at the wait one and set methods of this object shortly. Let's continue by closing up the class level objects and move on to look at the main method. I started out by creating a new iScheduler object and also references to an iScheduler job and an iScheduler task. And the next line of code, we're going to make a little segue here because we need to go look at a local private method named findHeadNode. And that method, actually, you can see from my hover here, returns a string. And I just would mention that I think one of the really cool features of this code we're going to look at is the fact that we're going to connect to the head node of the HPC cluster in a generic way. And that means that we should be able to take this code and run it on about any HPC system, no matter how large or small. So let's close this up temporarily and go look at that find head node. This is actually code I found in Microsoft sample code for HPC. I guess I would consider it more or less of a black box that just works. But it is a very important piece of code that enables us to run an HPC application on more than one cluster. And so what this does is basically goes out and finds the name of the current cluster in the Active Directory. The comments say bind to current domain, search for all version 2 head nodes in the current domain, enumerate head nodes, and then finally at the end of it is the return of a DNS name that's returned to the caller. Now that we found our cluster head and we're going to return that string, let's go back then. Let's close this up and go back to the main method and continue on where we left off. The first line inside of this next block calls the connect method of our scheduler object and passes it the cluster head name that we found in that previous find head node call. If that call fails, we catch a system.net socket error down here at the bottom, or a generic system exception, and if it's something besides a socket connection, we just generically write that to the console. If all goes well and we get a connection to the cluster head, then we write success of that to the console and continue. Right in here is where the real work of HPC begins. Scheduler.createJob returns a job object. We can name the job and, most importantly, wire up the .onTaskState and .onJobState event callbacks. These events fire and call back when there is some type of state change at the task or job level. Now that we have a job, next we call job create task, and that returns us a task object back. And finally, we're at the one line of code that states the type of this task that we want is a parametric sweep. Since parametric sweep is an iterator, we set up a start value property, and we set that start value to 1, and we set up an end value property by reading from our app config file and pulling the value from number of cores. That's over here in app config, and I just set up a configuration there of number of cores, value 40 right now. Then to go on and explain, the cluster then uses the end value property of this particular parametric sweep task to dynamically determine how many machines and cores to use for the task. It does correlate to cores rather than machines, so by experimentation I found out that unless you specify a number larger than the number of cores available in the cluster, the head manager, when it fires up the job and the task, is not going to necessarily use all available resources. So I found out using a larger number, larger than the number of cores available, is the way to go. Now, probably what we're actually going to do here, what we're going to run, is the task.command line, and that's pulling a share location out of the app settings and then adding to that a call to the executable HPC blackjacklab.exe and passing a star as the first parameter in the task end value. So that star is a replacement then that HPC environment automatically iterates between the starting value and the ending value. Next thing that goes on here, there's only a few lines left. We add the task to the job with job.addTask, and then we go back and call the scheduler.submitJob method and pass it our job, and then we also pass a username and optionally a password. In this case, it's not necessary to pass in a valid password. You can pass in null and it works because of the trust that I've set up in the domain. And 2 more lines of code. I set a start time because I want to really track how long this whole job takes to run. And then here's this very interesting little manual event.wait1 method call right at the end. And I'll hover over that, and it says this blocks the current thread until the current system threading wait handle receives a signal. And that signal, by the way, we'll look at a little bit later, is the .set method. So really that's it as far as the scheduling and starting the job is concerned. Everything else really revolves around the task and job state callbacks. Let's look at those next. I'll collapse my main method, and let's look at task, which individual task callbacks happen multiple times, where the job state callback happens at the end. When I mentioned earlier that the parametric sweep task could be changed by changing part of one line of code, I was actually referring to line, I think it's 65 here, that we went through a little bit ago. And so since that line sets up the command line of the task, all you have to do to change that to some other executable is just change the name, and perhaps, you know, set up other app settings that you need to use. So let's go start analyzing the task state callback. That's one of the important methods. One of the first things we see here is that the sender coming back can be cast back to an iScheduler interface. Then from there we also need to pick up new state from the args that come back as part of this callback. And we can say if the task state is queued from that new state, then console write line that state, and if it's something else, then console write line that state. One of the main blocks here within try catch is looking for when the task state is finished, and in that case you can actually get a handle back to the task by saying scheduler.openJob, because args contains a job ID and a task ID. So combining scheduler openJob and openTask with those two arguments, you can get a handle back to the task. And console write line that we've got a handle back to that output of the task. And that's really one of the things that makes this task state callback unique to this job. Even though I said you can change one line of code to change the task, the callback here is still specific to the application, the executable that I'm running. And most importantly, you get a handle to that blackjack operation program standard out or console out through this task.output property. So from there, when you've got a handle to task output, really the rest of this code in the try catch block from here down to the bottom is really just taking the specific output coming back from an iteration of running a bunch of blackjack hands and setting some of our class level accumulator values, and then going on to the next one. So that's really it. Not very many lines of code there for a task state callback. So the next thing to look at then is the job state callback. At the beginning of it, we're actually looking for a job state value of canceled, failed, or finished, and in any of those three cases we're really going to be done and out of here. So here again is this little interesting instance object called manual event, and we call the set method on it, and the hover over that says sets the state of the event to signaled, allowing one or more waiting threads to proceed. And this is actually pattern code I found. You can set that and then go ahead and handle the job state finished. And you'll notice here I'm setting a stop time so I can do the math to come up with an elapsed time of stop time minus start time. And then again, basically the rest of this code again, this only happens once because it's the end of the job, but this is going to read then the accumulated values and format an output screen that on a character-based console is going to look something like this down here. And you might wonder why I did it that way. Well, it's because the output of my original Blackjack Lab program looks exactly like this, and just as a matter of style, I wanted the two to look almost identical so that it looked like there was some continuity between the two. And really, that's it. We're down to the bottom, and there's nothing really anymore to explain here unless somebody has some questions at this point. We can go back through some or all this code a second time and look at it in more detail, talk about it if you want, but otherwise probably my plan is just to go ahead and fire up a demo of my own specific HPC environment and the actual operation of running my Blackjack program. If we want to go ahead and start on that, let's look at Microsoft's terrific HPC management console first. I'm already connected up to a machine that's the head of my cluster named Mustang, and this is the head node. I'm going to zoom that up full screen, show you quickly that this is a HPC server install. There it is, Windows Server 2008 HPC Edition Service Pack 1. And there's a control panel here that comes from, I mentioned this early on, that there's an HPC pack install. So this is what the cluster manager looks like. There basically are 1, 2, 3, 4, 5 functional areas here: configuration, node management, job management, diagnostics, and charts and reports. By default, I came in here on node management, and this list you see, because I've chosen all nodes up here at the top, is the list of nodes in this cluster, and also which ones are online and active. As you can see, I've basically got my head node that we're on. I've got these one broker, this group of compute nodes, and I've got 2 compute nodes and one of my laptops that are offline. Skywalker is the machine that we're on, and it's a quad core. All the rest of these machines that are online are actually on one server. That's a dual quad hyper-threaded Xeon, so there's 16 cores available there, and basically 4 cores on Skywalker. I've actually got this Toshiba i7 based laptop offline on purpose. It has 8 hardware cores in it, and things run quite a little bit quicker with it, but I didn't want to overstate things tonight, so I decided to leave that turned off. And we don't have to spend a lot of time going through this functionality, but I think it is important to understand all the work that Microsoft has done here to help somebody out in configuring and maintaining a HPC cluster. This really is quite an amazing control panel. Right from here, for instance, you can go over here on the right hand actions and add a node, and there's a wizard that allows you to choose, do I want to add nodes or broker nodes that have already been configured? You can click on that and go next. And if you had pre-configured nodes, you could wire them up right here with just a couple of clicks. So there's a lot of really cool functionality in here. I probably will just go back and go through some of these briefly so you can see what kind of capability is here. In the configuration area, there's a whole list of configuration items here. The deployment to-do list, I've already completed all of these, as you can see. And there's a wealth of information right here. You know, for instance, just to pick one of these, add an operating system image, you can actually image an OS image to help you quickly deploy additional machine nodes. Going on to the network functionality, you can actually configure your network largely through wizard-based step at a time. Save a report about your network configuration. Nodes have templates, so each kind of machine type has its own node. Like there's an Azure node I told you earlier. I played around a little bit with that. Broker node template, compute node template, workstation template, and head node template, and you can make changes to those. I haven't done any of that. I've basically left all of these settings like they came out of the box. Here's the images functional area for like creating or capturing an image, and that's a machine image. There also are templates for job, and you can create your own custom templates. I'm using the default. I've not found any reason so far to change away from the default. Under the users area, I have everything set up as administrator, as you can see, which seems to be, for me anyway, an easy way to run this. You can add users, add administrator over here on the right. In the services area, I haven't said anything much about it so far, but there's some pretty cool functionality in HPC that's been added as a plugin around Microsoft Excel, and there's some really neat examples out there on the web of running macros inside of Excel and actually scaling those up and running them on an HPC cluster. If that's something that interests you, you can do some research on your own about that functionality. Here's an iSCSI deployment area, and this is where you can set up basically iSCSI storage for centralized storage for your cluster. Resource pools must be a way to separate resources by name on your cluster. Have not experimented any with that, but I see that there is help in here and wizards to help you do that. And this again, this functionality on the left is just part of the configuration tab, if you will. So going on to the node management, we looked at that, but there are different ways to group by here. Like if you want to see just the ones that are basically online, you can filter that way. 3 of them are online, but they're actually down, and so they can't be connected to. And there's an unapproved one that's Azure. If I wanted to connect that node back up to the cluster, I could right click and say start, and it would add it back to the cluster and allow me to put it online then subsequently. So each one of these functional areas, I guess to summarize, has quite a bit within it. Job management, when you actually schedule a job, and we're going to do that in just a little bit. When you schedule that job, it tracks in here, and you can see it as it's running by choosing active. There's finished filters, failed filters. If we look at like the finish list, here job 879 is one of the last of them that was run. Then you can get task, job details, an activity log of what went on during that task, and it's all very point and click oriented here, pretty simple to use and understand. Under diagnostics, there's actually a suite of tests that you can run to test the health of your HPC cluster. I've done those several times. Seem to work fine. Take a while to run, so we won't run those tonight. There's also a charting and reporting area. I believe I haven't researched this extensively, but there's actually a SQL Server database running alongside of this that is used to store a lot of this historical configuration information. And let's see, what else? Have I forgotten anything really that I wanted to show there? I don't think so. I think we can probably go on from here. At least that's a high-level overview. Unless somebody's got some particular questions, I guess we could stop for a minute or two here. If you've seen anything that I've clicked on that piques your interest and you want some more details about it, we can make an attempt here, since this is a live cluster, to poke around a little bit. It's up to you. As I've stated earlier this evening, the central theme of tonight's presentation is really all about a parametric sweep task. But in order to see how an HPC cluster improves performance and how things scale, you do have to have an example to work from. So because the only thing I've got running so far is a blackjack simulation, we need to first set a baseline target of this application running standalone so that we can see the performance increase in HPC. So my 1993 version of Blackjack Lab I've got running in DOSBox, and the reason for that is simply because 16-bit software, in other words QuickBasic written back in those days, will no longer run on 64-bit. So DOSBox is a DOS emulator that will run 16-bit software. Blackjack Lab is the program where you set up, for instance, the number of decks you're going to play with, shuffle with how many cards left. The most important one here that we're going to be experimenting with tonight is how many hands do you want to play in automatic mode. We're going to start this little demo by running 2,000 hands in the old piece of software. We're not going to do any card counting. I've got that turned off with this adjust bet using others tens ratio. That's basically card counting. So if we back out of this, and just quickly while I'm here, edit strategy databases. This is all based on the dealer's up card that you can see. So for instance, the weakest dealer's hand is a 6 up. When the dealer has a 6 showing, your hard standing number is 12, your soft standing number is 19. You double down on 10 or 11 when you have them as a player, etc. So you've got a rules database in here basically you can go in and configure. That's enough of that. If I go back and actually run the blackjack operation program, start out with a bet of 1 and then turn it loose to run automatically, it's going to go through 2,000 hands here in just about exactly a minute and a half. Some of the interesting things that come out of actually doing this over a period of time is we're tracking the longest winning and losing streaks, which even on 2,000 hands you're going to find kind of interesting. The bottom line number that we're tracking here is actually the win or loss percentage, and you can see right now we're in the negative numbers because this is red. You'll see a wide variation on 2,000 hands. You really have to run a large number of hands before you see that number stabilize for any given set of rules that are set up in here. We're already up to about 1,300 hands here, so let's let it run just a little bit longer. And again, we just have to have some kind of a benchmark to go by so that we can see the improvements that are coming with HPC. I have actually the DOS box environment and the way we're running this right now does limit it some. I should say that probably the fastest I've seen this run on a standalone operating system in a quad core is probably about 8 to 9,000 hands per second, and that was with 32-bit Vista on a quad core. It seems like going beyond that, the performance has been going actually down on hardware, probably because of Windows 7 and 64-bit. So here we're done with 2,000 hands. The longest losing streak was 12 hands, so believe it or not, and that's not that unusual. It's not that unusual to have a losing streak of 10 on 2,000 hand sequence, and I always see the winning streak being less than the losing streak. And in this particular sequence we lost 4.435% of our bet. I know what the actual average of this is on a large number of hands. I won't let you in on that secret until we've actually run this some in HPC. But again, this example took a minute and a half to run 2,000 hands of 16-bit software. So we'll leave the setting. Part of the reason for showing this is the fact that these databases are integrated, so if I change the number of hands in here and then go run my HPC software, it'll run this many hands. So right now, let's go do that. This will be the first example of running something on HPC. I've got a batch file here. All the batch file does is change directory to the Blackjack Lab subdirectory and then call the command line HPC Blackjack Lab runner.exe. That's the compiled version of the code that we looked at just a little while ago. So all I need to do to run that is start a DOS window and drop that batch file in it. Now remember, we're going to only run 2,000 hands here. There's our connection to the head node. We're already starting running and returning jobs, and there it did 2,009 hands in 3 seconds. And our loss percentage was 2.94%. That's actually closer to the average, by the way. We actually had a longer winning streak than losing streak here, which is somewhat unusual. And if we want to run it again, we can up arrow, run it again. This time we ran 2,022 hands for a loss percentage of negative 1.41%. We had longest winning streak of 10, losing streak of 9, and we did this in 2 3/4 seconds. Let's go back and log back onto the head node. Fire up the manager, go to job management, and look at this last job we ran, and we can say view all the tasks, and then we can actually here see this one as a master record for a parametric sweep task. Please select individual subtasks to view their output, and we can step down now and see that this 1.1 first iteration of the parametric sweep task actually ran on Mustang Comp 1. Here's the details of it. Here's the command line that was passed, and the result, this is actually the console out that gets sent back in the task state, task completed event handler. So no big deal, we just ran 2,000 hands, but that's no fun. We did it in a short amount of time, but it's really kind of a waste of resources doing that small a number. So let's minimize this. Let's go back to our blackjack management program. So let's say we might as well go up to 100,000 right off the bat. We're going to do this in powers of 10 from here. Well, now we change the number of hands we're going to play, and that's all we've changed. Let's open up a DOS window, drop our batch file in it. Now we're going to run from 2,000 to 100,000 hands. Oh, how about that? 3.4 seconds. You can see we've got a lot of overhead in setting up these jobs and tasks in the HPC cluster, and so it really is scaled for spending more time on those 40 individual tasks. But we need to raise this quite a bit before we're going to start pushing the cluster at all. So now we just ran 100,000 hands in 3 seconds. Now let's go back. Let's use another factor of 10, so let's go to 1,000,000. 6 zeros. Fire up another DOS window. And it still only took 3 seconds to run 1,000,000 hands of blackjack. Well, you would think that if I raised that another factor of 10, going from 1,000,000 to 10,000,000, that we would start to make a dent in the cluster, and actually we can see some change when we go to the next level. If we took our 3 seconds, or 3.5 seconds, and multiplied it by 10, we might think that we'd be going up there around 30 seconds or a little bit more. So let's go do that. Let's go back into our general settings here and go 10 with 6 zeros. DOS window. This time when I run this one, I'm going to hit Control S briefly so you can see the start of this. It says this is some of our console output. Found the following 1 head nodes, Mustang head, connected to cluster, and then we start sending in jobs. And it's interesting, we stopped the console timer here, so we apparently ran all these hands in a very short amount of time. That's just because we stopped the timer. The cluster was still running the hands, but the timer wasn't running. So to get a true, let's just up arrow that and run it again. This time we won't disturb it. Now we're running 10,000,000 hands here. But look at that, it only took 5 seconds to run those 10,108,098 hands for a loss percentage of negative 2.84%. Look at the winning and losing streaks. This is something that, if you're at all interested in blackjack, and again, this isn't the point of the demonstration, but when you run longer sequences of hands, you see these long losing and winning streaks, and those are legitimate. I've checked, double checked, triple checked, and quadruple checked the code over a number of years and know that that's right. Anyway, let's bump it up again. You would think that 5 seconds would go to 50 seconds if we were running 100,000,000. So let's do that. And actually, in this case, we're going to run out of decimal places here, because back when I wrote this, I couldn't imagine that I'd need to be running any more than 99,000,000 hands of blackjack, because at that time it took a day to run 1,000,000. So we need 100 with 6 zeros. 1, 2, 3, 4, 5, 6. And that's as many decimal places as we have. So fortunately, this will begin to make a little bit of a dent in our cluster. Remember, I'm missing 8 cores here because I'm not running that Toshiba laptop. Alright, here we go. This will take a little bit longer. You can see that the task callbacks, where it's sending back these numbers from the individual iterations, they're coming back slower now. It's all dynamically handled by the cluster manager. These get scheduled and come back somewhat randomly. So here we are with 31 seconds and 100 million hands. Now that's pretty impressive. Of course, this is a character-based app. It's not a GUI. Makes a lot of difference. And here we're at negative 2.81%, and I believe that's very close to the actual average. That doesn't change much if you go to a billion. I won't bore you with running a billion hands. In order to do that, we have to go in and manually edit one of our text files because we're out of digits in our character-based manager program. Now, since we've run 100 million, let's go back to our management node. And spend just a few minutes looking at this job in a little more detail. In the activity log now, I can see that I've scheduled this on the head, all of my compute nodes, and all 4 of my Skywalker quad-core cores. So I'm using 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 14 cores to... Oh, that's interesting. It didn't use any of the 4 cores on Comp A. That's actually kind of strange. Oh yeah, it did. I miscounted. 4 Skywalker cores and 4 Comp A cores. So we've actually got 4, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 cores that we're using. If I double click on this task, then I can see that I've got job details, and I can save that job as XML. I can view the tasks. We looked at this again, but here again is 1 through 40. Here's the 40th console out, instance 40, total number of hands to play. In this it was 100 million. Number of cores to use 40. Number of hands to play in this instance was, let's see, that's 2.5 million. I've got statistics on resource selection here. I've got statistics on the allocated nodes for this task, licenses, environment variables, etc. It might be more interesting to get one of these to fail, because if you have failed, then you can actually go in and see what failed. That doesn't happen very often actually, but I have had a few errors based on running out of connections, which I think is a DOS or a workstation server limited number of connections to about 20. I've seen a few of those errors. I doubt if we can force one of those tonight. Anyway, that's kind of gives you a visual of how jobs can scale from single core, single machine, UI-based applications like I wrote back in 1993, and how those can scale up to HPC and be run on a cluster.